Most people use or come across essential oils in everyday life. Have you ever wondered what these oils actually are? What makes them smell? What they're composed of? In this experiment, you will use gas chromatography to analyze a sample of rosemary essential oil. Gas chromatography, also known as GC, is a very useful tool used in chemistry for separating and analyzing the different components that make up a sample. In order to perform GC analysis, you need to have a sample that is in the gas phase. This means that your sample has to be able to be vaporized without decomposition. This experiment will utilize GC to separate the components in rosemary essential oil and then analyze them by flame ionization detection, also known as FID. Its three main components will be determined. GC uses two phases to separate a sample. A mobile phase, which is an inert gas like helium or argon that moves the sample through the column, and a stationary phase, which is the microscopic layer of liquid polymer that coats the inside of the column. As the mobile phase and the sample are moving through the column, the different analytes in the sample will interact with the stationary phase. If an analyte has a low affinity or attraction to the stationary phase, it's going to pass through the column relatively quickly because there's nothing to slow it down. If an analyte has a high affinity, it will have a greater interaction with the stationary phase and therefore take a longer period of time to pass through the entire column. This is essentially how separation occurs with gas chromatography. Once a sample has been injected into the GC, it's vaporized at high temperatures, typically 200 to 300 degrees Celsius, in the injection port. Once it's in the gas phase, the mobile phase and the sample move through the column, and this is when the separation of the different components occurs. As the components then elute from the end of the column, they flow through a detector, where the concentration of each component is measured as a function of time, and this is what gets displayed as a chromatogram. The time that it takes for an analyte to travel through the column, from the injection port to the detector, is called the retention time, usually abbreviated as RT. Every compound has its own characteristic retention time that's dependent on its unique molecular characteristics, such as the boiling point, molecular weight, and polarity. As long as all the GC parameters are kept constant between runs, such as the flow rate of the mobile phase, the oven temperature, and the stationary phase material, the retention times for a specific compound are going to be constant. This allows for the identification of specific compounds, and the comparison of retention times is what gives GC its analytical usefulness. There are many different types of detectors that you can use with GC, and in this experiment we will be using a flame ionization detector, abbreviated FID. It works by burning the now fully separated sample and mobile phase in a hydrogen-air flame as they exit the column. As the different components in the sample burn, they lose electrons and form positively charged gaseous ions. These ions are attracted to a negatively charged detector plate, causing a current of electrons to flow, which is directly proportional to the amount of compound. This current is collected, amplified, and converted into an output. The type of samples that we're going to be looking at today are called essential oils. They are a natural oil that can be obtained from plants. They can also be referred to as volatile oils, called volatile because the components in them readily vaporize into the gas phase. This property makes them the perfect choice for GC analysis. They are super concentrated. For example, it takes 16 pounds of fresh peppermint leaves to produce just 1 ounce of peppermint essential oil. There are important ingredients and flavor additives in many familiar everyday products, such as candies, syrups, toothpastes, cleaning products, skin creams, lip balms, and cooking spices. They're also commonly used for medicinal purposes, aiding in the treatment of sunburns, headaches, insect bites, and nausea, just to name a few. The specific type of essential oil that we're going to be looking at is that of rosemary. Rosemary is a common herb and a member of the mint family. Its name is derived from the Latin words ros, which means dew, and marinus, which means sea, or dew of the sea, because in many locations it needs no water other than the humidity carried by the sea breeze to live. Rosemary essential oil is commonly used in many industries. For example, in traditional medicine, it has an old reputation for improving memory, and also as an antioxidant. Antioxidants are molecules which inhibit the oxidation of other molecules, so because of this, rosemary oil is also a very good preservative agent. In the pharmaceutical industry, it's being investigated for the prevention and treatment of diseases such as cancer, coronary heart disease, and even Alzheimer's disease. It's commonly used in cooking, as well as in perfumes in the cosmetic industry. This is an example of a chromatogram that's been produced by rosemary essential oil. As you can see, there are three main components, evident because of the three main peaks. You will be identifying two of them using the standards provided. Since retention times are constant if the GC parameters are the same, if a standard has an identical retention time to that of one of the three main peaks, you can say that that standard is present in rosemary essential oil. For the third, you'll be searching through previously published literature and using your knowledge of how the GC works to propose what you think the third component could be. Once this lab is completed, you are going to be able to do four main things. The first is to be able to draw out a schematic of the main components of a GC. The second is to be able to use your knowledge of how a GC works to explain how the separation of different components in a sample occurs. The third is to be able to predict how different molecular characteristics cause an analyte to have a longer or slower retention time. Lastly, you are going to become familiar with looking through a scientific paper which has been provided.